that I paused on Wednesday and then I could hit play right now, we are picking up right where we left off. And I'm not imagining that we recall, hence the warm-up question. So in this packet, if you could turn to the last page, page 4, and can we answer number 6? Number 6. And can I share, just to make the calculation a little more speedy, that the molar mass of potassium chlorate is 122.55 gram per mole. So this is gas stoichiometry, not at STP. That's where we paused at the end of Wednesday. Okay, go for it. Our answer is 13.5 grams of potassium chlorate. Do not worry if you're still calculating. So those are supposed to be waves. I know it looks like lips. Imagine. What did you think of the question? A mustache. No artistic ability. Maybe you thought like, oh, what? What day is it? What do I do with this information? You can always start, if we're ever stuck, when in doubt, and you take the information you're given and go to moles. Now, of course, is that what you should do? but that's always a consideration. So you have, right, a volume of your gas, a pressure, a temperature. Oh, we need moles for stoichiometry. If you want, you can go the route of P equals nRT. Whenever we're problem solving, we're going to be applying that a lot. But remember, you do not have to. You could employ the combined gas law. I have both sets of work. So if we did ideal gas law, now we have to be sure that when we're applying the ideal gas law, that we just obey the units that R brings in. I don't convert any of these. I'll convert these if needed. Oh, great. We're already given atmospheres, liters, and Kelvin. So I'm getting moles of oxygen, and then I can go right to my Stoich. But also, what you could do is first solve for what the volume would be at STP so that you can use molar volume. And you'll get the same answer either way. Questions for me? So back to our unit packet. And I just wanted to show you, not a sign, not a sign, not a sign. We were looking at these problems that are under the page of gas Stoich, yeah? That's when we hit the pause button. The next page, there's a handful of practice problems if you would want, and then I've included my work in the answers. All right, so where we are picking up, we've talked about this, but I want to relate partial pressure to mole fraction. We haven't done that yet. So what we're accumulating is like a series of maybe options when we're problem solving. So we know we have our basic gas laws, V1, P1 equals V2, P2, V1 over T1 equals V2 over T2, and so on. But collectively, we could just apply the combined gas law, and then if pressure is constant, it's just volume and temperature, and so on and so on. So we have combined gas law, we have P equals nRT. We talked about mole fraction. If it's mole fraction of gas one, then it would be moles of one in relationship to total moles. Mole fraction does not have a unit. Moles of oxygen don't necessarily cancel with moles of the mixture, but we just acknowledge that moles will cancel. Mole fraction is a value less than one, because this is a part of the whole, right? Well, if it's only one gas, it will be one, but we're dealing with mixtures. And so this is more a value that we do in comparison. So for example, the mole fraction of nitrogen in our air is definitely greater than the mole fraction of O2. So then how do we interpret that? Well, there's more moles of nitrogen present than there are oxygen. I'm just making these numbers up. Maybe the mole fraction of nitrogen is 0.7, and maybe this is 0.28. Well, then we have more nitrogen here than we do oxygen. So it's a comparable value, even without a unit. We just compare in ratio to one or in ratio to another mole fraction, if that makes sense. Okay, the ideal gas law, PV equals nRT. Well, you don't have to do this. What if I want to solve for N? Obviously, right? So PV divided by RT equals N. Well, we're saying mole fraction, if we're looking at, let's say, gas one, is moles of that gas over total moles. Okay, well, couldn't I say, if I'm looking for moles of gas one, if it's all in a mixture, they'll have the same pressure total. They'll have, I'm so sorry. No, they'll have P1 and then total volume same, total temperature the same. And if I'm looking for total moles, wouldn't it be pressure total times overall volume divided by RT? So can I plug this in? Absolutely. And so what we get is mole fraction is equal to P1V over RT divided by PT, meaning total pressure over RT. And so we know we can simplify. Those cancel each other and volume cancels each other. So mole fraction, yes, is a ratio of moles, but it also can be the pressure of that gas, partial pressure, divided by total pressure. So we just have another way to relate it, another way to find. So easy peasy equation. Just as one example, could we look at example 3? I betcha you can just dig in and solve it. I'll solve it simultaneously, and then we'll check in with each other. A torr is 1 and the same with millimeters of mercury. A torr is 1 and the same with millimeters of mercury. We can keep it torr or millimeters of mercury. Concerns? Okay, so, and kind of new relationship, but based on ideal gas law relationship. Do we need another minute? We collect gases over water into vessels. In your unit assignment, there's problems that involve that, but Zumdahl never did the teaching for that. So, a very old edition of his book, he did address whenever we have liquid water, we have to account for the partial pressure of water. Yeah. So we did that the other day. Here is the teaching on it because it's absent from your chapter.
Not that you need this, but if you feel like you do need more support after we do, so I'm just turning past that, the problem after those pages. But very, very importantly, I'm removing the part. So third line down, after time of the reaction, that we're going to stop that sentence and just cancel. That was presented, not expecting us to remember, in honors chemistry, but usually we adjust things so there isn't a height difference. So we can just ignore them. Promise, promise, promise. All right. Stoichiometry. Britton, I knew you were going to love this problem. Okay. If we take a look, I know Stoich, I need the reaction. Could you please provide the balanced chemical equation? God bless you.
HCl equals MgCl2 plus H2.
Absolutely fantastic. Not that phase symbols are not required. I like to place them because it just helps you make sense of the givens. Magnesium in its elemental form is a solid. We're given that it's an 8 molar solution of HCl. Magnesium chloride is soluble. I know it doesn't have any of the always ions, but it is soluble. Okay, the hydrogen that was produced was collected over water in a eudiometer. A eudiometer is just a big test tube, if you will. We could also call it a gas collecting tube or a vessel, a container. That's it. A eudiometer, though, allows us to perform electrolysis. It has electrodes at the anyway, so that's where that comes from. All right. So we collected it over water. You know, I like to have a picture. You definitely don't have to, but I'm imagining a bin of water. And so I know that as the reaction is going, I'm collecting the hydrogen. But I know wherever liquid water is, there's water vapor. So there's going to be also some water vapor there. Oh, by the way, have we ever addressed? We say water vapor, but we say hydrogen gas. Why don't we say hydrogen vapor or water gas? Okay, what do you mean naturally exists? When do we see the gas form? Or are we at STP? No, I hope not. Sorry, that was a little bit funny. Sorry. I know, right? So body temp 37, 0 Celsius, that would be not very comfortable as we are dressed right now. Okay, so no, but we encounter it under room conditions, lab conditions. So room temperature and pressure and room temperature and pressure. So that's why hydrogen gas, oxygen gas, nitrogen gas, water, we mainly found as a liquid. So that's why we attach vapor. So just a little trivia that may help with problem solving. Okay, so, we know the volume of the hydrogen, 32.85 milliliters. The temp, 22 degrees Celsius. And we're told the barometer read. And remember, Rishi so excellently reminded us that we use a barometer to measure atmospheric pressure. So I'm just going to label that as P with a little ATM because it's the atmosphere, is 742 millimeters of mercury. For me, the reason why I'm putting it over here is I don't want to assume it's the pressure of the gas. So I'm going to put it over here so I don't just grab it when I'm problem solving. Determine the mass of the magnesium reacted. Oh, the partial pressure of water at 22 Celsius is 19.8 millimeters of mercury. So we know the volume of the gas. We know its temperature. We're doing stoichiometry. What should we do? Isaac? So pressure of the atmosphere, where's the pressure of the atmosphere? I'm talking about the pressure of the hydrogen and water. Why? You're right. But isn't the atmosphere exerting pressure on the outside? I'm trying to get the inside. So the understanding, if we're not told there's any height difference, we know this started filled with water, but the collection of the gas displaced it, pushed it out. We would definitely assume there is no height difference. So the level on the outside is equal to the level on the inside. Well, why is this level this level? Well, the volume of our water, but we know that the pressure of the gas in the atmosphere is pressing on the outside, and this gas is pressing on the inside. It must be the same pressure. If it wasn't, there would be a liquid level difference. If the outside pressure was greater, then this liquid level would be higher because it would be pushing down more strongly. If this was greater, the liquid level, the gas inside would be lower. Yeah. Isaac, does that make sense? Okay. So if we know the pressure on the outside, we're saying that's the total pressure of the mixture. So you are exactly correct. We take the 742 and subtract away the partial pressure. Excellent. So the partial pressure of our hydrogen. $722.2 millimeters of mercury. We were looking for the mass of that. We have the volume, the temperature, the pressure of the gas. And we just jump into the stoichiometry or begin. We're starting in terms of gas. We're not at STP. So here's where you make the choice. Do you choose ideal gas law or combined gas law? Yes. Just like we did in the warm-up. Are we? I want to just provide us the answer. I know we can do this because we just did it in our warm-up. I find it nice and handy. I'll make sure we have it. Oh, I'm not going to find it easy. So are we good from there? I'll make sure that I have the problem solving. Are we good to move onward? I know we are. Okay. So next, the speed of a gas, the velocity. We know velocity is speed with direction. Okay. We know temperature is an average of the kinetic energy. And so we talked about the Maxwell-Boltzmann distribution, yeah, number of particles, and then if we want to say kinetic energy, that there's going to be a spread. And we know that we're going to have some that are very low, some that are very high, and then there's like our average. Well, the same with speed. If kinetic energy is the energy of motion, this applies also to velocity. It's an average. Okay. Root mean square. My favorite explanation of what root mean square velocity is, Zumdahl gives us. The average velocities of the gas particles is a special kind of average. Oh. What we're doing is we're taking the square root of averages that were obtained doing the square root. That's all. Okay. You can look at this. It's mu root mean square velocity, or you can call it cursive V. Totally fine with me. All right. But this is a wonderful equation. Didn't we already address that the speed of a gas is a result of the temperature of the gas? Now, Zumdahl uses capital M for molar mass. I like capital M. So I'm afraid we're going to call that molarity. I don't think we would, but just in case. So know that in your textbook, he uses capital M, and you can see either MM or M. Those are used interchangeably, so I prefer that. So the higher this value, the greater this value. The greater this value, because we're dividing by it, the smaller this. Didn't we say the heavier the gas, the greater the molar mass, the slower, and the greater the temperature, the faster. So if you would be given a question that said you have a sample of hydrogen at 200 Kelvin and a sample of oxygen at 100 Kelvin, no, sugar, and a sample of hydrogen at 100 Kelvin, which will have the greater speed, well, wow, there's a difference of 100 Kelvin. So I would definitely say we don't even have to look at molar mass. The greater the temperature, the greater the speed. Oh my gosh, I think I still had oxygen there. I changed it to hydrogen, so then I've eliminated this difference, and so we can see the role it would play. But what if this was oxygen at 200 Kelvin compared to hydrogen at 200 Kelvin? Well, then the greater molar mass would be the lower speed. So if you're asked that in a justification question, what more proof do you need than this equation? So yeah, we could say, well, the greater the molar mass, the lower the speed. But couldn't we say, according to the equation, or citing the equation that I wrote to the left, okay, there's something we have to be on guard for. I will tell you, dealing with gases, this is the most common mistake that I see. You know, I give you equations. I give you them. In P equals nRT, the R gas law constant, we apply 0.08206 liter atmosphere per Kelvin mole. Period, end of story. I will provide those. That's the easiest. But that is not the value we apply here. It's still the gas constant. How can we call it a constant but it has different values? Crazy. Someone just made it that way. I know it does not make sense. The R here is the other form that we'll apply when we're not dealing with gases, but here we apply it. 8.314 joule per Kelvin mole. Okay, so we take 3 times joule per Kelvin mole times the temperature, which you know will be in Kelvin. Okay, so Kelvin cancels. We'll have joule per mole, molar mass, gram per mole. So moles cancel. We're taking the square root of joules, and then we get meter per second. Go ahead, sir.
Then the mass can include from the grams from the molar mass, and then you just have the speed squared and then the squared.
We can define a joule as 1 joule would be 1 kilogram times speed squared. You're absolutely correct. Absolutely correct. So why don't we just re-express joules as that? Thank you, Damien, so much for leading us. Well, then we're taking this times 3 times Kelvin. So Kelvin will cancel. So here's the other most common mistake. Using the different R value here, but do you see what unit we need on our molar mass if we keep usually molar mass, golly, 99% of the time, 99.5% of the time, gram per mole. But to make it work with this equation, we need our molar mass. This is where we forget to be in kilogram per mole. How can we forget? I'll give you that. We just have to make sure we're not ignoring it. So we cancel the Kelvin. Well, then we're going to end up canceling mole and kilogram and taking the square root of speed squared, so meter per second. So the heaviest gas, quote unquote, the heaviest gas, it's unbelievable that it even is a gas. Neon, somewhat familiar with that. What if we had sulfur hexafluoride? That is a weird exception because such a high molar mass, you would think it would be a liquid at room temperature and pressure, but this is a gas. If you have a balloon of sulfur hexafluoride, it falls to the floor very, very quickly because of its great molar mass. What if we are asked for the speed of it at room temperature? Okay, let's obey our equation. Our lightest gas would be hydrogen. So look at the span of molar masses that we can have. So hydrogen, oxygen, nitrogen, those will be thousands of meters per second. But if we just pause for a moment, every 1 second, one chemistry, 1 second, this gas, a meter is like your wingspan. So let's see, if we started measuring here, where would 226? Would that be at the edge of what, Rolling Hills Park? Is that what we call this? Sorry, right? Isn't that what the park is called here? Okay, Rolling Hills Park, like to the barrier or to the edge of that. In 1 second, that's pretty outstanding. Pretty outstanding. Good. So we'll either solve for speed. You can also be asked to apply this to get molar mass. So you just have to be careful with your algebra, be careful with your units. And then we can also use it to back up theoretical statements. Okay? Okay. Just to start the thinking, we'll come back to this on Monday. So it's page 22. 2 minutes. Okay. We know really these equations only truly apply to ideal gases. Gases that we say have no particle volume. Remember, that's kind of the big leap in the kinetic motion theory of gases, and no particle attraction. And we can help a real gas really minimize those by being at a high temperature and then low pressure. But we're not always at that. We do a lot of experimentation at low temperature and high pressure. And under those conditions, a real gas strays from that. And so if we apply this to a real gas at those conditions, and we try to solve for the volume, it's way off. If we apply this at high temperatures, the pressure is going to be off. So, never have to memorize equations. This is the van der Waals equation. Don't have to know that's what it's called. Okay, so we adjust 2 terms. Because moles don't change, right? If you're at a different pressure or temperature, that'll just be the temperature, and R is a constant. So what changes when we have real gases to account for that when we just apply this, we get pressures that when we measure it are way off. Volume that when we measure it, we're way off. So what we have to know, there is one problem in the unit assignment that asks you to apply the van der Waals equation. So I have a sample here. And then you're just plugging and chugging, and we'll talk about what A and B are. But more so, we need to know theoretically, why do we do that with P? Why do we do that with B? So we just make some adjustments, and then we can apply it to real gases. So we found a way. Pretty good, pretty good. Ideal gas law serves us most of the time. You would only apply this if you were asked. Apply the van der Waals equation or apply the equation below. Okay, so we'll touch on that Monday. We'll talk about Graham's law of diffusion and then start to practice. Tuesday, we will pick back up with our redox titration. Wednesday, problem solve. Our calendar has us assessing this unit Thursday. Okay,